After studying this module, you shall be able to know about mixed SN1 and SN2 mechanism. Acquire factors influencing SN1 and SN2 mechanism. You will be able to identify the borderline cases. You will be able to evaluate parameters leading to a mechanistic borderline. You will analyze factors governing reaction mechanisms. First, we will have an introduction of nucleophilic substitution reactions. In a nucleophilic substitution reaction, a nucleophile, which is electron-rich species, bonds with a positive or partially positively charged center in a substrate, expelling the leaving group. The two factors, that is molecularity and reaction kinetics, classifies nucleophilic substitution mechanisms as substitution nucleophilic unimolecular SN1 and substitution nucleophilic bimolecular SN2, where the SN1 mechanism is a two-step mechanism involving carbocation intermediate, whereby the product of the reaction is a racemic mixture, and the SN2 mechanism proceeds in a single step through a transition state, whereby the reaction leads to inversion of configuration. Example of SN1 mechanism is shown here. Tertiary butyl bromide reacts with water to give tertiary butanol. SN2 mechanism is reaction of ethyl chloride with bromide ion to form a transition state which expels chloride ion, which is the leaving group, to form ethyl bromide. This is an example of SN2 mechanism taking place in a single step. There is only difference in the timing of the steps between SN1 and SN2 mechanisms. On one hand, in the SN1 mechanism, first the leaving group leaves followed by the nucleophilic attack, whereas in the SN2 mechanism the two things happen simultaneously. But sometimes under a given set of conditions there are reactions that are known to proceed with a mechanistic borderline region, that is mixed SN1 and SN2. Example of mixed SN1 and SN2 mechanisms is this shown here. This benzyl substituted chloride reacts with sodium methoxide in presence of methanol to form this methyl ether. Classically, these two proposals defined the mixed SN1 and SN2 mechanisms. First, neither a pure SN1 nor a pure SN2 mechanism operates, but some in-between mechanism is operative, leading to both inversion and racemization of products. Secondly, in the same reaction mixture, some molecules react by the SN1 while others react by the SN2 mechanism simultaneously. A research work was done by Schneen et al., according to which the entire SN1 or SN2 mechanistic spectrum could be fitted into a simple scheme involving ion pair intermediates, accommodating features of both SN1 and SN2 reactions. According to the proposed mechanism, the substrate is first ionized to an intermediate ion pair, which then leads to the formation of final products as follows. Rx forms R plus X minus ion pair, which then gives product. What can be inferred from this equation is that for SN1 mechanism, the formation of the ion pair is rate determining and rate constant is K1, while in SN2 mechanism its destruction is the rate determining involving K2 as the rate constant, and where the rates of formation and destruction of the ion pair are of the same order of magnitude, their mixed SN1 and SN2 mechanisms are observed. The experimental evidence suggests that the borderline mechanism or mixed SN1 SN2 mechanism were shown by benzyl chloride hydrolysis in aqueous solvents. The substitution proceeds with a clear SN2 mechanism. However, upon para-substitution, para-methoxybenzyl chloride solvolysis takes place by the SN1 route. As the para-substituent changes from the order of electron withdrawing to electron donating functional groups nitro, chloro, hydrogen, methyl, OCH3, a progressive change from the bimolecular mechanism to the unimolecular pathway is observed. The intermediate situation for para-methyl benzyl chlorides was found to be borderline, where it was argued that SN1 and SN2 processes occur side by side. With the addition of azide ions, good nucleophile, to the reaction, the alcohol is still there as a product. But 4-methoxybenzyl azide comes out to be another product. The role of additional nucleophile azide ion is thus to increase in the rate of ionization by the salt effect, but decreases the rate of hydrolysis. Thus, both SN1 and SN2 mechanisms were shown to be operative simultaneously. Previously, for a borderline mechanism, the most important indications were partial racemization and partial inversion of products. However, Werner and Schneen demonstrated that this type of stereochemical behavior is consistent with a strictly SN2 process where double inversion takes place, leading to racemization. In another view, Schleier et al. Proposed that solvent assistance to ion pair formation is the key to mixed mechanism behavior. Schleier et al. On the other hand criticized the ion pair concept of mixed SN1 SN2 mechanism suggested by Schneen et al. And proposed that there is a gradation of transition states between the SN1 and SN2 extremes with varying degree of nucleophilic participation by the solvents. The borderline region was considered to be one where nucleophilically solvated ion pairs were involved, which basically looked like the transition state of SN2 reactions. With the recent study of reaction kinetics, it was led to an argument that nucleophilic substitutions at saturated carbons occur by the stepwise SN1 mechanism, where the lifetime of intermediate carbocations decides reaction pathway. The term borderline therefore implied to the existence of a line separating SN1 from SN2 whose position depended on the lifetime of the reaction intermediate. When the carbocations exist in energy wells for at least the time of a bond vibration 10 to the power minus 13 second, SN1 mechanism follows, which changes to the SN2 mechanism if the energy well for the intermediate disappears. Here pre-association stepwise is shown, then pre-association concerted. The diagram C shows liberated intermediate. These are the reaction coordinates with intermediate lifetimes for nucleophilic substitution. This schematic representation conveys about reaction coordinates that distinguishes between mechanisms based on lifetime of intermediates. It is only unstable or the steady state intermediates which were considered to not accumulate during the reaction. Basically, two borderlines were considered. First, A, between mechanisms where intermediate does not play any role and mechanisms that depends more on intermediate in a stepwise manner. Secondly, between mechanisms where the intermediate either does or does not have enough lifetime to diffuse through the solvent before reacting with a catalyst or another reactant. If, in case the intermediate does not exist or is too unstable to diffuse through the solvent, a pre-dissociation mechanism is followed in the reaction in which the reactants, be it the final reactant or catalyst C, they assemble before the first bond making or bond breaking step take place. Convincing grounds has been set for this hypothesis. Let us take an elegant example in which benzhydryl bromides were made to react with amines in DMSO dimethyl sulfoxide, giving benzhydryl amines, benzophenones and benzhydrols as product. For the reaction under several cases, first order rate constant K1 for the formation of carbocation were observed, which were similar in magnitude as the second order rate constant K2 for the concerted SN2 reaction. As the change is observed from SN1 to SN2 mechanisms when the lifetimes of the carbocations in the presence of amines were calculated, which came to be approximately 10 to the power minus 14 second. These parameters were used by the authors to calculate reaction pathway suitably enough for predicting the preferred mechanism of the nucleophilic substitution of benzhydryl bromides. Thus, the lifetime dependent switching of mechanism was confirmed. Here it is shown that benzhydryl bromide reacts via SN2 pathway with an amine and via SN1 pathway to give the products. In SN2 pathway, amine derivative is formed, whereas in case of SN1 pathway, an intermediate carbocation is formed first, reacts with the which is solvated by the solvent DMSO. That solvated intermediate then reacts with amine to form benzophenones, not the amine derivative. Whereas the aqueous workup of the intermediate gives the alcohol via the SN1 pathway. Next is the nature of substrate in deciding factor for borderline mechanism. Primary and secondary substrates generally react by the SN2 mechanism and tertiary by the SN1 mechanism. However, tertiary substrates seldom undergo nucleophilic substitution, as competing elimination is always a possible side reaction, and with tertiary substrate it usually predominates. In an experiment, relative reactivity of the different alkyl halides towards SN1 and SN2 reactions were determined. Methyl bromide, ethyl bromide, isopropyl bromide and tertiary butyl bromide were taken as the substrate. According to what is noticed is when passes along the series of halides from methyl bromide to the tertiary butyl bromide, the first and last member readily undergoes hydrolysis. On the other hand, the intermediates ethyl bromide and isopropyl bromide are somewhat resistant to hydrolysis. In the investigation of kinetics of the reaction, what was observed is a change in the order of reaction whereby the reactivity by the SN2 mechanism decreases from CH3 to primary carbon atoms, and at a secondary carbon atom the reactivity is so low that the SN1 starts to contribute significantly, rising sharply to tertiary carbon atoms. Experimentally, the rate of hydrolysis with dilute aqueous ethanolic sodium hydroxide gave this type of plot. This plot for the rate of hydrolysis with dilute aqueous ethanolic sodium hydroxide has two curves, and the substrates are methyl bromide, ethyl bromide, isopropyl bromide and tertiary butyl bromide. One curve is for SN2 mechanism and the other is for SN1 mechanism. For SN2 pathway, the rate decreases as we move from methyl to tertiary butyl bromide, whereas for SN1 mechanism, the rate of hydrolysis increases from methyl, that is a primary, to a tertiary butyl bromide. The minimum in the curve is attributed to a shift in the reaction mechanism from SN2 to SN1. Moreover, the effect of electronic and steric factor on transition state of each substrate was considered to explain this change of mechanism in each case. For SN2 mechanism, the enhanced inductive effect of methyl group makes the carbon less positively charged and thus less polarized. Hence, it is less readily attacked by the hydroxide ion. This inductive effect is, however, small as compared to the associated steric bulk, as a result of which hydroxide will find it progressively more difficult to attack a tertiary carbon than a primary carbon. The more crowded the transition state is relative to the starting material, the higher is its energy and therefore slower will be the reaction. Experimentally, for the reaction Br minus plus RCl under strictly SN2 conditions, as it was shown that the rate were relative SN2 rate for methyl chloride was 1. For ethyl chloride for SN2 reaction, the rate was 2.7 into 10 ki power minus 2. For isopropyl chloride, the rate is 4.9 into 10 to the power minus 4, whereas for tertiary butyl chloride, the rate is 2.2 into 10 to the power minus 5. Thus, the relative rate for SN2 reaction decreases with steric bulk. On the other hand, for SN1 mechanism, as carbocation intermediate is stabilized by both inductive and hyperconjugative effect of methyl groups, therefore, as the above series of halides is traversed, there is increasing stabilization of transition state, hence there is an increase in the rate of SN1 reaction. The observed hyperconjugative effect is maximum for tertiary carbocation, as there are 9 hydrogen atoms available for hyperconjugation. As for the steric effect, since the carbocation is planar with sp2 hybridization, so there is less crowding in the transition state than the initial sp3 hybridized alkyl halide. The SN1 mechanism is therefore preferred on inductive as well as steric grounds in the order of hydrogen least reactive, then methyl, then isopropyl, then tertiary butyl groups. Here the inductive effect and the hyperconjugative effect are shown. This explains the shift of SN2 mechanism to SN1 mechanism across the halide series shown here. The effect of structure on relative reactivity is quite evident when the leaving group such as halogen is placed at the bridgehead of a bicyclic system. The experimentally observed rate of solvolysis for the substrate in 80% aqueous ethanol are as follows. The rate of hydrolysis for tertiary butyl bromide is 1. For the other substrate, it is 10 to the power minus 6, and for the norbornyl bromide, it is 10 to the power minus 14. For these substrates, the reaction will go typically slowly due to unfavorable geometry of the intermediates in SN2 mechanism as well as ion pairing SN1 mechanism. This is because for bicyclic substrates, the backside attack is prevented owing to their sterically hindered location as well as case-like structure, which makes it impossible to acquire planar structure as is observed in both SN1 and SN2 mechanisms. Now we will study a comparison between SN2 and SN1 mechanism and the competition between them. Due to stability of intermediate carbocation formed, primary alkyl halides prefer to undergo substitution by SN2 mechanism, whereas tertiary alkyl halides by SN1 mechanism. However, secondary alkyl halides, benzylic and allylic groups may undergo substitution either by any single mode or even the experimental conditions may lead to a mixed substitution mechanism. The experimental conditions that determine which mechanism will predominate, whether SN1 or SN2, are concentration of nucleophile, second is reactivity of nucleophile, other is solvent. These three factors or conditions will determine whether the reaction will undergo via SN1 or SN2 pathway. First, let us study the concentration of nucleophile. The rate law for SN1, SN2 and mixed SN1, SN2 reactions are as follows. For SN1, rate is equal to K1 concentration of substrate. For SN2, rate equals to K2 concentration of substrate multiplied by concentration of nucleophile. Whereas for a mixed SN1 SN2 reaction, rate equals to K2 concentration of substrate multiplied by nucleophile concentration plus K1 concentration of substrate. The rate law equations make it clear that an increase in concentration of nucleophile increases rate of SN2 reaction but having no influence on SN1 mechanism. Therefore, when both reactions compete with each other in a reaction mixture on increasing the nucleophile concentration, the fraction of reaction that takes place by SN2 mechanism is the more preferred one. In contrast, the decrease in nucleophile concentration would decrease the fraction of reaction that take place by SN1 pathway. Next is the reactivity of nucleophile. The nucleophile participates in rate determining step in SN2 mechanism. Therefore, with the increase in reactivity of nucleophile, the rate of SN2 reaction increases by increasing the value of rate constant K2. As more reactive nucleophile would displace a leaving group in a better way. On the other hand, there is no effect of nucleophile reactivity on SN1 mechanism. Therefore, a poor nucleophile would undergo SN1 mechanism and a better nucleophile will increase fraction of SN2 mechanism when both reactions are competing. Next is the solvent effect. If the change in concentration of nucleophile has no effect on the rate of a reaction, then it is SN1 reaction. If there is an effect, then the reaction must be SN2. A remarkable role is played by the solvent properties on the rates of the two types of reaction, SN1 and SN2. If the solvent is nucleophile in a substitution reaction, the process is called solvolysis. For such reactions, it is difficult to predict the mechanism that whether it is SN1, SN2 or mixed mechanism, as the reaction would follow a first order kinetics due to excess of solvent present, rate will be equal to K multiplied by concentration of Rx, the substrate. This is because for SN2 mechanism, the concentration of nucleophile will remain practically constant throughout. As being solvent, it will always be present in large excess. Therefore, it becomes difficult to predict nature of mechanistic pathway based on stereochemistry of products. In general, polar solvents with high dielectric constants, water 81, ethanol 25 and acetone 21, increase the rate of SN1 reactions. This is because in SN1 there is formation of intermediate carbocation where solvent facilitates the stability of separated ions, which would lower the activation energy for this step, thus enhancing rate of reaction. Therefore, increasing the polarity of the solvent will decrease the difference in energy between them. In turn, increasing the rate of the reaction, as shown here in this figure, the free energy versus progress of reaction is plotted. In one case, the transition state is more highly charged, case 1, reactants are less highly charged. In case B, the transition state is less highly charged, whereas the reactants are more highly charged. A represents reaction coordinate diagram for a reaction in which the charge on the transition state is greater than the charge on the reactants, whereas the B represents reaction coordinate diagram for a reaction in which the charge on the reactants is greater than the charge on the transition state. For SN2 mechanism, polar solvents stabilize the reactants more than the transition state, as the charge is more dispersed in the transition state. Therefore, polar solvents slightly decrease the rate of SN2 reactions. If the charge on the reactants is greater than the charge on the rate determining transition state, a polar solvent will stabilize the reactants more than it will stabilize the transition state, which will increase the difference in energy between them. Consequently, increase in this polarity of the solvent will decrease the rate of the reaction, and shown in figure B. Now, let us summarize what we have learnt so far. Based on experimental conditions, nucleophilic substitution reaction take place strictly by SN1 or SN2 mechanism, or a mechanism borderline between the two substitution nucleophilic pathways. To explain the borderline mechanism, two theories were proposed, that either a unifying intermediate ion pair mechanism is functional, or in a reaction mixture both SN1 and SN2 runs simultaneously. Based on lifetime of intermediates, the term borderline implies to the existence of a line separating SN1 from SN2. When the intermediate carbocations exist in energy wells having at least the time of a bond vibration approximately 10 to the power minus 13 second, SN1 mechanism follows, which changes to the SN2 mechanism if the energy well for the intermediate disappears. The nature of substrate play central role in deciding mode of nucleophilic substitution. whereas based on electronic and steric factors, it has been established that substrates with primary carbon undergoes SN2 mechanism and tertiary carbon undergoes SN1 mechanism, whereas secondary carbon may choose to take either of the mechanism or might as well exhibit borderline mechanism. Both inversion and racemization of products occur in borderline mechanism. Mixed kinetics with additive rate law is operative for borderline mechanisms. For substrates with bridgehead carbon, nucleophilic substitution are difficult to take place. Increase in the concentration of nucleophile speeds up the rate of SN2 mechanism when both SN1 and SN2 mechanisms are operative and competing simultaneously. Good nucleophiles drive competing reactions in favor of SN2 mechanism. Polar protic solvents speed up rate of SN1 mechanism by stabilizing the intermediates. Polar protic solvents decrease the rate of SN2 mechanism as they stabilize reactants better than the intermediate transition state.